Good afternoon. My name is Nick Samus. I'm excited to be speaking today on cybersecurity in space, sharing some considerations for designing space systems for mission surety. I want to share a brief background so you can understand where my perspective is coming from. I started my career as an aerospace safety engineer, specifically working in flight critical safety avionics. I pivoted after a couple of years of my career to cybersecurity. And for the bulk of my career, I spent doing analysis in industrial control systems and otherwise non-standard mission support systems as a security analyst. I currently serve as an adversary emulation engineer with a MITRE corporation, where we pursue the science of how adversaries affect systems, primarily through cybersecurity means. The problem for critical space missions, as I see it, is concisely put as our traditional design processes do not adequately identify risk because our threat landscape has so significantly changed. When we started designing systems from a safety engineering perspective decades ago, the complex nature of our systems and the interconnectedness that cybersecurity threats pose to our systems today were not generally a concern. We generally applied a safety-only approach, and what we're seeing evidence of today is cybersecurity is able to affect those safe missions. In short, we can't assume that at the top of our fault trees we're building that safety is an and with security operations. We are seeing evidence that security has the ability to affect safe missions. We tend to focus on systems and components rather than focusing primarily on data, and this has led to a lack of understanding of our mission dependencies on computed data. And the last tenet of this problem I see is that resiliency, which is kind of a de facto word for mission cybersecurity, has largely been interpreted as a reactionary measure. What I think we need to do is shift our focus into more of a proactive measure so that we understand that resilience is a trait that we should build into our systems and we need to plan for. We can't simply rely on hoping that response and recovery capabilities can be executed after it's too late. I do want to call out ahead of time here that there are ongoing efforts in this area. There have been academic approaches presented that address specific elements of this entire problem. And I want to specifically call out the proactive approach that specifically EASA has demonstrated. They are addressing head-on the fact that cybersecurity risks can pose a threat to our as-designed systems in civil airspace. And I see the work that they are doing as an exemplar effort. The general trend I'm seeing is that we are attempting to move left in the system development cycle and trying to consider cyber as early as possible, which is a positive change. The 2 points I want to particularly focus on in this presentation are a paradigm shift for us in being firstly data focused rather than component focused, and second, ensuring that the defensive mechanisms that we're identifying as appropriate are actually effective for our complete mission set. I don't think the answer is going to be a single addition of a new analysis into our current process that's going to fix all of our problems. A little bit of background is necessary for this conversation, and I want to share. The first is what I'll refer to as the human element. I'm by no means an expert in human factors. It's a discipline in and of itself, but I've analyzed enough missions and seen enough disconnects in missions where the humans play a critical role. Oftentimes we design systems and humans are the afterthought or simply just users of the systems. But I think it's important for us to understand that humans are inherently a component of the systems we're building. From a data-centric perspective, rather than just a component focus, humans are both a source and a sink of data. That is, we inject data into systems for system control and response, and we are inherently affected by data systems give back. And protecting against human operation is not trivial. We're seeing this as a large challenge when we're dealing with complex systems that we're creating. Knowingly or unknowingly, humans are able to put systems into states we've not necessarily designed for. And this is arising because as our systems are continuing to increase in complexity, so does the situational awareness challenge of bringing complex data sets into human understandable sized data pieces. A quote from a NASA report specifically referring to safety considerations on Air France 447 that I think codifies this well is, only when design and training respect the day-to-day limits of human comprehension and team performance can reliable operation continue. And all of this is knowing that we're not yet even in the face of a motivated adversary for cybersecurity. Thus, when we add cybersecurity into the mix, our challenges are only going to get greater. The second piece of background that I want to touch on lightly is that cyber is in fact impacting critical missions. I don't have a lot of time to go into detail here, but it's safe to say that operational missions are regularly being affected. And humans, while we specifically serve to defend against cyber attacks, they also serve to perpetuate cyber activity. This is how humans can affect our missions from a cybersecurity perspective, again, willingly or unwillingly. There is increasing evidence of targeted attacks, and this is a core characteristic to show how our threat landscape has changed and continues to change over time. Not only are we only facing adversaries that are using opportunistic attacks, as an example, ransomware. If I'm a motivated adversary and I'm financially motivated to steal money, I don't necessarily care who I'm stealing that money from if my goal is met at the end of the day. But what we're seeing is an increased appetite towards targeted attacks on the other end of the spectrum. An example of this is the Triton scenario from mid-2017 on a Saudi-owned petrochemical facility. This is an exemplar scenario because it does in fact identify that adversaries are increasing their level of effort to go have specific targeted effects. And this also proves the point that safety critical domains are being affected. I'm very cautious here to not overstate the consequences or otherwise effects that Triton did exhibit, but it is accurate to say that cybersecurity did indeed have an effect on safety critical hardware in that instance. So moving forward, how is this happening? How did we get to this place? And in short, the primary reason we are here is that our safety analyses were never scoped to readily consider cybersecurity implications. As our threat landscape has changed and the increased digitization of our systems that we're building, the concerns that we're facing today were just never something that we thought to build into design. First, safety engineering focuses on proper system function under expected conditions. It's generally physics-based. We explicitly do not focus on malicious intent to affect data. And second, I think an important piece to note is the common cause analysis, which is a general technique to identify when one single failure may contribute to multiple issues in my system, for lack of a better term. They may not be scoped for cyber means. Oftentimes we use the term dissimilar hardware and software, dissimilar design, but if we're looking in the face of a motivated cyber adversary or generally cyber systems, our dissimilarity needs to go beyond hardware and software. It needs to consider network, crypto, or protocols even potentially. This misunderstanding or misrepresentation, so to speak, is an issue even in the absence of malicious intent based on the threats we're facing today. In short, our safety analyses do not readily consider these cyber dependencies because of these shortcomings. So shifting focus into the space domain, which is what we're all here to talk about, I think it's important to define what are space systems. And it's not just the rovers, the telescopes, the space vehicles at the end of the day. Certainly they are the pinnacle of our engineering design and achievement, and those are the things that are actually executing the mission of collecting data or pushing the human footprint out beyond Earth. But it's more than just those space vehicles that we need to consider. There's significant support infrastructure from ground station communications to enterprise support to the infrastructure that supports all of those infrastructure components. Space systems support our everyday life. From cell communications to commodity GPS, we are seeing that our everyday reliance here, terrestrial-based, is increasingly reliant on space-based communications and inherently space-based systems, including space vehicles. With the rising wave of 5G and pervasiveness of IoT, this is only furthering the convergence of our reliance on space-based systems. In order to deal with that increased required throughput, we are seeing a convergence of similar hardware and software design. And over time, as we increase both the access and operational knowledge of how these systems are working, that inherently creates an increased risk for our space systems. So moving into cybersecurity itself, I want to set the stage that not all cybersecurity is created equal. What I mean by that is there's not a single set of cybersecurity guidance that we can apply across the board to every mission holistically. It's certainly appropriate that some guidance can be applicable across domains, but blindly and transparently applying one set of guidance or industry best practice into a domain where it may not be applicable is simply not appropriate. On the top left here, starting with the NIST cybersecurity framework, the 5 functions serve as a good core framework to build upon. And generally what we do is we identify industry best practices or specific controls that I can enable in my system. And we generally, once applied, we generally consider those cyber secure systems. There are best practices that we can follow. In this example here, I've listed a couple bullet points that I think present unique challenges to the space domain. I'll admit I cheated a bit in what I chose here, and these are not only unique to the space domain, but what they are unique enough from traditional enterprise cybersecurity guidance that they do require some unique guidance. In this case, I think all of these characteristics relate specifically to the industrial control systems domain. It's where I spent most of my career, and we absolutely have some best practices and lessons learned from that domain that we can apply to the space domain. So building on that, it's appropriate to say that ICS can serve as a good surrogate for space, but it's not 100% compatible. And to illustrate that point, I want to call out how we would define an appropriate response plan in space. If we look at that guidance directly from NIST, from Special Publication 882, a direct quote on the bottom here is that incidents are inevitable and an incident response plan is essential, which I agree with, and it's something that we certainly need to proactively design for. However, if I look at that same guidance, the same document for guidance on how we could actually implement an appropriate plan, here's 2 data points that may not be appropriate for space systems. One, how would I physically isolate a space vehicle under attack? Do I need to actually sever physical links if I'm able to? And second, how would we, quote, manually operate with all external electronic connections severed? Unless we have significant change to the way we're designing systems today, it's just not compatible guidance. What we are seeking is best practices that are specific to our space systems. I was happy to see earlier this year, in September 2020, SPD 5, Space Policy Directive 5, named Cybersecurity Principles for Space Systems, was put out. And as I read SPD 5, this is exactly what it's asking for. It's not an authoritative document on thou shalt go execute these processes, but to me, it's a call for space best practices. As we see in this diagram, if we start from the left, we've got a whole host of cyber problems for the systems I'm building. If we utilize ICS as a surrogate domain, we can apply some ICS best practices that broadly apply. But there are also some challenges beyond ICS that are specific to the space domain we need to consider. And herein lies the problem that SPD 5 is trying to address. What I do like about it for certain is that it's a push for a design integration. 2 specific bullet points out of SPD 5 are a call that space systems extend to Earth. As we called out, the terrestrial reliance is paramount to making sure we're scoping our space problems appropriately. And second, applying best practices where we can from other domains. What's still needed in my mind, however, is a more concise definition and scope of what those unique challenges are. And second, how we can learn from currently deployed systems in order to document requirements for our under-development space systems. Moving forward, here is a single slide where I'm going to do my best to describe the unique characteristics in space in about 2 minutes. Realistically, this probably requires its own presentation, but I want to call out a couple characteristics in space that I really think set the stage for why it's unique. A couple obvious ones to begin with, we're certainly dealing with costlier consequence and increased mission timelines. When it takes 6 months for my space vehicle just to get to the place where it can start its mission, I'm certainly dealing with timelines that we don't necessarily address in other domains. Second, it's a wireless by default domain for us in space. We have traditional out-of-band challenges. Now, it's certainly appropriate to say we've addressed this before. As an example, cell phone systems, as we've built and used and come to rely on a daily basis. Cell phone systems are wireless by default also. However, when a space vehicle has a software or hardware malfunction, I can't simply shut it off, take it out of orbit, and drag it into the Horizon shop to fix it. I've got to build in some preventative mechanism to address that. Which brings us to the first point. There's a significantly limited solution space for remote or otherwise deployed maintenance. This creates a large challenge for us because the general practices for response and recovery that require physical interaction are generally not going to be possible, specific for our space vehicles. Further, any maintenance that requires some downtime may actually have some detrimental effect on our mission if we don't plan for it ahead of time. Second, I think the most important characteristic here that defines space uniqueness is our highly abstracted picture of what situational awareness is. In most other domains, I can physically sense or build in additional out-of-band communications to sense and validate the sensors that are actually pulling in critical information for us to build a sense of reality from. In space, it's not so easy. From the technological challenge to the physical constraints we're dealing with, we inherently have a significantly increased, a significantly abstracted picture of what situational awareness is. Putting all of these together, to me, the unique strategy that space is really requiring is starting with the response and recovery ideas. It's safe to say that our space systems are going to rely on unique, maybe newly designed response and recovery mechanisms. And knowing that, it's inappropriate for us to expect that traditional guidance from other domains in the identify, protect, and detect functions from the NIST CSF will be able to support unique response and recovery mechanisms. So to this end, I think it's imperative we start with response and recovery goals and inform our unique protection and detection capabilities that our space systems must be designed with. So all is not lost, but now is the time to start doing our work. As a reminder, adversaries cannot break physics, but they can break and attack our implementations and assumptions. And this is exactly where adversaries try to live. If it was not made abundantly clear before, everything hinges on the data. Modeling and validating our models of these data flows serve to provide a reference against which we can measure trust or normal operation of our systems, so to speak. We can build these models and populate these models because we own the mission and the terrain. We're able to build defensible infrastructure that our missions are reliant on. But I want to offer a word of caution here. We have come to live in a dashboard-obsessed world, where in cybersecurity green means good and a complete pie chart is how we measure success. But that cannot be our sole end goal. We must consider the utility and the relevance of what we're monitoring and the detections we're building and the relevance to our specific mission. Further, if we can't collect it, it can't be monitored. We must ensure the architectures that we're building are in fact monitor capable. We need to monitor for both malicious activity as well as expected operations. And this is the linchpin for how we build the link of relevancy back into our mission context. So immediate actions. I want to talk about some in progress or otherwise immediate actions we can take today. The first that I want to highlight is engaging the community. 2020 was a great year. Associated with the DEF CON conference, we had a Hack-A-Sack competition, which otherwise brought in some additional adversary thinking, provided some awesome, unique diversity of thought, bringing in people that may have not had access to look at space systems prior and actually experiment on a representative testbed system that was set up. What that was able to do is help push our thought on identifying unique threat scenarios we have maybe not yet uncovered. The single piece of guidance that I would offer mission analysts and owners, for one thing to start doing today, is the second bullet, and that is acquire and develop adversary thinking. This helps us perpetuate identification of those new threat scenarios, which will ultimately allow us to result in a more sure mission set. Key here is ownership and not outsourcing of that adversary thinking. We'd be foolish to think with the seismic shift that we're going through in our threat landscape today that we'll magically be able to handle continuous changes in that threat landscape over time after a few outsourced pen test engagements. What is key to success is acquiring and developing that adversary thinking internally and owning it so we can create continuous process improvement. What do we do with that adversary thinking is we start with high-risk areas. If we've got a system diagram, as an example in the top right here, let's look at a critical function, look at all of the data that's going into it, and assume the adversary is affecting that data. If you're familiar with casualty analysis, start identifying elements and effects from confidentiality, integrity, or otherwise availability effects from the data elements that we've identified. And lastly, collaboration is totally critical here. Our adversaries have caught on to the fact that complex systems require interdisciplinary skill sets in order to attack, and we'd certainly be wise to share our adversary thinking across those teams and defend these systems with interdisciplinary skill sets as well. And beyond, how do we work beyond what's next? In my mind, we should strive to codify mission understanding and implementation. As an example, requirements are not enforced via paper policy. And generally we take credit for them, but if they are not enacted on, if they're not actually instilled into the system design, oftentimes they can go unnoticed. As an example, a common requirement I see is only one logged in user shall be present on any running instance of the remote client at a certain time. And oftentimes we see that as a paper policy and something that an operator or network defender, say, can go look for. However, a more proactive approach that we should be striving towards is actually codifying a monitoring or otherwise protection rule, either not allowing the system to get to a state where number of users is greater than one, or alerting when the case happens. An exemplar effort I do want to call out here is the Top 20 PLC Secure Coding Practices effort. It's now an officially recognized ISA initiative, started from a couple members of the industrial control systems community. And while they're focused on secure PLC practices, what I really think they're doing at the end of the day, knowingly or not, is working to codify mission understanding. What that does for us is it allows for the detection of two things. First, physical possibility, and second, mission plausibility. If we recall that adversaries cannot break physics, physical possibility becomes a great measure for us to use against how our systems are actually operating. When we're getting to the limits of physics, we may need to consider something might be wrong. And second, again, as we own the missions, we generally understand what plausible mission functions look like and how they operate. Using all of these, what we're seeking to do is verify potentially untrustworthy mission-critical data flows in our systems. And I'll end on a challenge for change. Our future will require assured autonomy. Designing for the operation in the face of adversaries is necessary, and as our systems become increasingly more complex, appropriate design foundations today will support and will reap the benefits of mission surety in the future. I'll leave on one final thought. That is to change the value proposition. If our primary goal is increased security, and the concept that I've really identified on how we do that is through heightened monitoring and contextual understanding of data, there are tremendous side benefits that benefit not only security. And this is how we can gain momentum by changing that value proposition. The infrastructure we're building as requirements for security today can easily be seen to benefit increased efficiency for mission operators when they're debugging problems, or reduce downtime required from misunderstood data flow or unexpected behavior. That increased awareness that we're reliant on for security is not only supporting security at the end of the day, and there are significant benefits throughout the organization that we can leverage with that increased awareness. At the end of all this, I hope that one thing is clear, that increased visibility into our missions via monitoring first will be an enabler for validating trustworthy system data. Moving forward, it needs to become a non-negotiable requirement for mission surety. And with that, I thank you all for your time, and I thank AIAA for the opportunity to present my thoughts here, and I look forward to continuing these conversations at the Ascent Conference. Thank you.